Okay, the final piece of the puzzle is we're going to be investigating the behavior of a function around a root, right? So root is also another name for an x-intercept, right? So roots are basically x-intercepts. And in this case, it's intercepts. And in this case, different x-intercepts can have different behaviors of the curve, all right? So let's consider an equation in factored form, and I'm going to look at three cases for you. Okay, and if this is one of the factors of each x-intercept, of each function, sorry. Okay, there's going to be some kind of power associated with each factor. Okay, now we can understand that, right? If this is part of a function, f of x is equal to, let's do x minus a times x minus b times x minus c, right? If it's some kind of function that includes x minus a, we know that a and 0 is one of the possible x-intercepts, because we know that an x-intercept will occur when y is equal to 0. So in this case, we would let f of x equal 0. Okay? So we know we have an x-intercept for all these cases, and it's a and 0, but however, there's going to be different ways that the graph will behave around those x-intercepts, right? So when you have a power of a factor, right, this power is called the order or the multiplicity, okay? So the order or multiplicity is related to the power of each factor, power on a factor that can be used to determine a root, right? A root, or also known as an x-intercept. Okay? So a power of 1, you can say it's an order of 1, right? So the order is basically 1 in this case. And an order of 1 tells us that the graph, the behavior, right? The graph will pass through the x-intercept a and 0, right? So what that really means here is, this is our function. I'm just going to show you what an order of 1 will look like. Okay, so this is our graph, right? And let's say that this is our x-intercept, okay? So let's say this is a and 0, and if a graph passes through or slices through an order of 1, then it just looks like that. It can look like that, or it can go the other way around, right? It just goes through it, is what it's saying. Okay, and you can basically add to our notions of other aspects of behavior, right, that we looked at, like the end behavior and so forth. And this would help you to draw a much more a refined sketch, really, right? So we know that an order of 1 would mean that the graph will pass through a root, right, or slice through a root. If we have an order of 2, right, if we have an order of 2, that means that the power on the factor is 2, then what the graph is going to do here is the graph will bounce off or be concave to a and 0. Okay, so I'm going to show you that. So this was an example of an order of 1 root, right, or a multiplicity of 1. Let's take a look at multiplicity or an order of 2. Okay, let's say that this is our similar x-intercept. Okay, so this is a and 0, and if you bounce off an x-intercept, right, you could have a curve that looks like that, right, or you can have a curve that looks like that. Okay, so this is what an order or multiplicity of 2 looks like. Okay, the third scenario, we can have an order of 3. So in this case, a graph will have a point of inflection. Right? The point of inflection is a change in concavity at x at a and 0, the x-intercept. Okay, so this is what an order of 3 looks like. Okay, so I'm just going to kind of construct that out. So I think you'll get a better picture of this, and I think the best way to kind of get a better picture of this is to do example questions. So really stay tuned in my further videos where I do show you guys examples of this stuff, right, and how it just kind of intertwines together, all right? But for the most part right now, I'm just kind of introducing this concept. Okay, so here is a point of inflection, okay? And the other case, okay, it can look like that. So you can see that it changes concavity, right? You're going concave up and then concave down and then concave up. Okay, so that's what a change in concavity is. In the other scenario, you can go concave up and then concave down, right? This is concave up, concave down. Okay, so that's what an order of 3 is. So these are essentially what we call orders or multiplicities. Right? It's really useful to understand what our behavior is around the roots, and you can tie this in with end behaviors and get a much more clearer picture of what your sketch will look like, right? We also mentioned earlier that, and I'm just going to add a page here, but we also mentioned earlier that you can also find extrema between the x-intercept, the midpoint of the two x-intercepts, right? So this is something I want to highlight, right? Like for instance, if this is your sketch of your graph, let's actually do a different sketch here. Well, sorry about that, guys. Okay, so if this is the sketch of your graph, okay, and you can notice here that this would be an even function because you have similar end behaviors. You have negative infinity and negative infinity, right? And you can find that the end behaviors are in quadrants 3 and quadrants 4, right? So this tells us that this is a negative even degree function. So it's a negative even degree function. And you can notice that if it's a negative even degree function, this guy has, looks like, 3 turns, right? I'm just going to highlight the turns in a different color. Right, there's a maximum here, there's a minimum here, and there's a maximum here, right? Because it's an even degree function, we have a restricted range, right? And this would represent an absolute maximum point, right? This would represent a local maximum point, right? So remember that for even degree polynomial functions, you will have an absolute maximum or minimum depending on if the a value is greater or less than 0, right? If a is greater than 0, we have an absolute minimum. If a is less than 0, we have an absolute maximum. Okay? And we can notice here that there are 3 turns, right? So this is a local minimum. And because there are 3 turns, we can notice that one of the turns can be determined by finding the y-intercept. Excuse me. But the other turns you can determine by finding your x-intercepts. Right, specifically the midpoint of your x-intercepts, right? So this is, we can notice that there's 4 x-intercepts here, right? And for all intensive purposes, right, we can say that this is x-intercept A, B, C, and D, right? And in this case, you can notice that for all of these factors, all of these factors should have a power of 1 because of the fact that the graph actually passes through them. It slices through these points, right? So it's really advantageous to look at functions in their factored form, right? So that's one of those things that we will kind of allude to later, right? That a polynomial function in factored form will give us a lot of information regarding its behavior, right? And it helps us to sketch it better, right? And we also noted that the midpoint of these x-intercepts represent turns, right? We can call this turn 1, we can call this turn 2, right? This guy's already given, so we don't have to worry about that, right? So the x value of turn 1 here is the midpoint of a and b divided by 2, right? And the x value of turn 2 here is b plus c divided by 2. So this is just a really quick way of determining or approximating where you would find your extrema. Now the best way is using calculus, right? But we're not, this is a separate course, right? You'll learn this further in different math courses that you will take in the future. And if you find the x value of the turn, you can just plug in to the function to find the y value, right? So this is basically your y value of your turn, b plus c over 2, right? So in conjunction with knowing the behavior of each root, right, you can also figure out, but using the roots to find the points of extrema. So hopefully now you have all the tools that you need, but I think the best way to kind of understand this is by doing questions. So that's what we're going to be doing in the next upcoming videos.